design design scheme for emulator-friendly emulation verification IP to accelerate simulation performance. The solution as the design size increases, system SoC, system on-a-chip SoC level simulation consumed a lot of time consumed a lot of turnaround time TAT. So one of the simulation to address this state TAT consuming to speed up the verification through the co-emulation. However, while the emulator can accelerate the design under tested DUT, the non-accelerated test bench, especially the frequent communication over the memory interfaces between the memory verification intellectual property VIP and the design, acts as a bottleneck for simulation performance, thereby diminishing the effect of the latest TAT. To address this issue, we propose a method to accelerate the frequently communicate with the mem VIP on the emulator. We redesign the primary operation of the memory that operates with the universal verification methodology UVM component to the synthesizable form connected to the DUT and test bench. Experimental results showed that the redesigned approach achieved approximately 27 times faster simulation performance compared to the simulation time before redesign. This approach significantly reduced the simulation bottleneck, effectively lowering the TAT and enhancing the overall verification efficiency of the large SoC design. Introduction. As complexity of the size of the logic design and as in SoC design verification continue to increase, the verification process has become approximately the more intricate. So the one solution to improve the verification efficiency and quality and efficiency of the verification is utilized to the co-emulation with an emulator, which can enhance the speed of the verification. So, however, when directly using the test bench employed in a simulation with this context, it can sometimes be challenging to achieve the satisfactory simulation performance. This paper presents a method for early designing memory VIP, which involved the data transmission to be more emulator-friendly. This study examined the bottleneck inherent to conventional memory VIPs during the UVM testing on an emulator. Through the redesign process, we have identified methods that are not only allowed to fully use in correct typical simulation, but also maximize the simulator performance. The remainder of this paper is organized as follows. Section 2 introduces the methodology for performing the UVM test bench with an emulator and explains why the use of the UVM memory VIP from the simulation environment failed to yield the satisfactory performance in such an emulated setting. Section 3 presented the redesign methodology for the memory VIP aimed at maximizing performance within the emulator. Section 4 provided experimental results that are comparing the simulation performance and the redesigned memory VIP with that of the original. Finally, the concluding remarks are given in Section 5. Chapter 2 is enhanced the UVM test bench performance. Can we boost the execution in emulator? A. Background UVM test emulation. The basic principle of the testing in the emulator involves accelerating the desirable duty and in the emulator. While not a synthesizable UVM test which operates in an emulator, a simulator. The test bench is conducted through the communication between the emulator and simulator. The process known as co-emulation to facilitate relatively easier testing of the UVM test bench in an emulator. Electronic design automation EDA components provide various emulator options such as Veloce SVTP, bring up, system value, bring up mode. B. Challenges in memory VIP in co-emulation. In co-emulation, some of the most critical issues that make it challenging to maximize simulation performance when running UVM tests used simulation is frequently uh, interactive between the accelerated DUT in the emulator and non-accelerated memory VIP in the simulator. This interaction can prevent the test bench from the effectively capturing the performance benefit of the emulator. As a result, through the improved test bench performance, although the improved test performance can be achieved compared to simulation, it is difficult to attain a satisfactory speed when compared to verifying the actual memory device board connected to the emulator. This consequently makes it challenging to pre-validate the operation of the SoC before the actual memory is developed. C. The need to customize the VIP instead of the prepackaged VIP solutions from the EDA companies. However, EDA vendors who actively advocate for the co-emulation methodology may already provide a VIP suite for their emulators. Consequently, it's natural to pose the following questions. Should we not simply use the VIP that incorporated the co-emulation methodology provided by the IP vendors? The answer to the question can vary, yes or no, depending on the type of the project. From the perspective of the memory vendors, it's essential to develop next generation memories and corresponding associates quickly respond to industry trend. The specification of these memories are subject to frequent changes, and each memory vendor may employ a variety of their own special operations that are not defined in the specification. For instance, NAND flash memory uses several vendor-specific commands shared with the memory controller to enhance performance, which are not disclosed for confidentiality reasons, while the EDA companies can provide VIP solutions that are sufficiently accelerated on emulator. It is challenging for them to support that these undisclosed special commands promptly. Therefore, there is a tiny need for a customized model for they can incorporate the new features, offer superior debugging capabilities, and flexibly respond to unstable new functionality. Chapter 3 Key Idea Emulator-friendly Lee models of memory VIP. The core principle of the co-emulation acceleration is to improve the simulation performance by delegating the intrinsic role of the UVM driver or monitor to synthesize and be able to accelerate interfaces in the form of the functions or tasks. Based on this fundamental concept, we propose a VIP design scheme that is tailored to the performance characteristics of the memory operation. So the figure 1 depicts a schematic representation of the main idea of the Lee model's memory VIP and interface proposed in this paper. The A. Moving the memory operation from the driver to the interface with the appropriate size array. As mentioned earlier in section 2, the biggest bottleneck of the memory emulator is the frequent communication with the non-accelerated region. This leads to performance degradation in simulation, especially in cases of the high-speed data transfer like NAND and DRAM. To address these issues, you can reduce iterations by declaring an array of the transactions such as the size of each transaction fits within the bandwidth permitted by the emulator per unit time when transmitting transactions between the emulator interface and the simulator VIP driver by considering the size of the transaction that the memory specification can handle and efficiency of the bandwidth between the emulator and simulator. You can declare an adequately sized array within the interface and the size design an FSM2 controller. See Figure 3. Figure 1 is key idea of the design scheme for emulator-friendly memory VIP, memory verification IP. The figure 2 illustrated the configuration of the main operation finite state machine FSM. Detailed description of each state within the main operation FSM are as follows. Either the system is in an initialized state with no ongoing operations. The driver transition to the state derived by invoking trigger main FSM on the interface. In the case of the redo operation, the driver transfers each data array to the interface. Subsequently, the driver calls wait and wait underscore and underscore FSM via the virtual interface. Wait. In this state, the system awaits data transfer process corresponds to the read and write command drive. This state manages the data transfer between the interface and DUT, and if a state arises necessity halting the data transfer, such as the encounter back prior, the system transitions to the pause state. Upon the completion of the data transfer, the system transitions to the exit state. Pause. In this state, the system waited when host, such as a memory controller, cannot receive data. This pause persists until the data transmission becomes feasible again. Exit. All transmissions have completed or the transition has been terminated due to the command abort or similar event. The system transitions to the idle state in the subsequent cycle. During this phase, the wait and FSM task called by the driver through the virtual interface complete for a write operation. Upon the termination of the end FSM, the driver acquired the data array from the interface. The figure 3 explains the data transfer mechanism governed by the main operation FSM. As previously mentioned, the key to the accelerated simulation is to minimize the number of the communication between the hardware description language HDL and hardware verification language HVL side. The most straightforward method to achieve this reduction is to maximize the data transfers within the bandwidth limit permitted by the emulator. In this case of the OY write operation, all necessary data can be transmitted once at the exit stage. For a read operation, the data transfer occurs once at the idle state when a driver triggers the trigger main FSM task. The data transfer operation between the DUT, the confirming the memory specification, are executed in the derived status according to altering the current AC timing requirement. So figure 2 is the main operation FSM. Figure 3 is data transfer controlled by memory, a main operation FSM. Section B is overview. AC-timing models based on clock cycles. Another principal strategy for co-emulation optimization involves eliminating time-consuming regions in simulation and retaining the only in the untimed areas. Although the mentioned in section 2, it is possible to run the test even if there are time-consuming construction in the test bench using options provided by the emulator like Veloce StratoM bring-up mode. One must tolerate a performance drop. This is because the time-consuming regions in the simulations are monitored as events by the emulator. A key characteristic of the memory operation is signaling to meet the AC parameters defined by the device specifications. Implementing this often requires a time-consuming method typically realized through the Veloce delay statement sharp delay in a UVM driver's monitors. We propose an alternative method by embedding two specification AC timing models directly into the interface. The first model features on AC times FSM for the AC parameters that are activated when an emulator memory command is issued. The second model uses a shift register that handles AC parameters that are continuously applied during the data transmission, such as those associated with the strobe signals. Section C is AC timer FSM. The figure 4 illustrates the structure of the AC timer FSM in all states of the main operation FSM is set to follow either IC The consuming the corresponding to each state can be defined, thereby allowing the AC mod timer FSM to be triggered. After the main FSM set the desired AC timing and wait for it elapsed, it informs the main operation FSM that a delay has ended. This modification serves as a fundamental condition for training the next state within the main operation FSM. The description of each state of the AC timers FSM is as follows. Either this is the initialization stage, and the FSM can transition to the set state through the trigger from the main operation FSM. Set upon the receiving the AC timing with setting from the main FSM, the status update the counter to the wait for the specified delay. Count in the state the FSM count according to the specified AC timing. Check. This state checks the presents a linked AC timing by referencing AC timing list figure 5. If a linked AC timing exists, FSM transition set state to the wait to the AC timing. If there are no further linked AC timing, the FSM transition to the down state. Down. This state certified the main operation FSM that the timing has been awaited. In the next cycle, the FSM transition back to the idle state. Figure 5 illustrates a simplified example aimed at enhancing the understanding by depicting the management method for AC timing age list required for a NAND and read data transfer. Initially, the necessary timing for the read transfer each state of the main operation FSM, specifically the TDQSQ, DQS, DQSQ, DQS to last, DQ valid per access, T the TQ and the DQ and the DQ as a whole, the DQ as the first DQ becoming the non-valid per access, and the TCHG CE underscore N high to a high output high impedance are the sequential registers in the AC high timing list. In the set state, the system is computed to count the first parameters DQSQ. When the counting the DQSQ is complete, the count state in DQSQ is removed from the AC timing list. Subsequently, in the check state, TQH is checked and the system transitions back to the set state to await the next timing and repeating this process literally. So the figure 4 is AC timing FSM. Figure 5 is example of the managing the AC timing list. Section D is shift register and strobe generation. In the series of read operations, some AC timers are used on a one-time base, while the other H timings, such as those related to DQS signal and need to apply to every time for signal toggles. For instance, according to the JEDEC-defined NAND specification, DQ strobe signal must be toggled after a certain interval of the response to the read enable RE signal. This is defined in the NAND specification as DQ SRE data output RE underscore N2 DQS latency. Such a signal must be applied to every bit of the data transmitted within the single command. The specific H timing delays was implemented using the simple shift register as an FSM. So the figure 6 illustrated the operational principle of the shift register design for a signal, such as a strobe signal. By the shifting 1 bit per cycle, the signal is toggled upon reaching the desired target. To better understand this, consider the DQRES example previously discussed. Initially, the register point corresponding with the DQRS-RE interval is set to the target. Upon the occurrence of the RE signal from the host, it is sampled by the emulator clock and recorded in the first bit of the shift register. When shift register RE signal reaches the predefined target, the DQS signal generated. This shifting takes place every cycle and the described process is repeated with each occurrence of RA signal. Figure 6 examples of strobe generation by the shift register. The experimenter. Chapter 4 is experimental. A. Experimental conditions. To measure the simulation performance of the test, two metrics were used. 1. Simulation time left per hour in the period when a memory operation peaks. 2. Data transfer rate between the NAND controller SoC and the NAND using iometer measured by per second. Table 1 is shows the description of the experimental setup. The emulator used in the experiment in the Veloce StratoM from the Siemens with the Veloce OS version v23.0.2. The simulation to the Veloce was conducted using the Quest simulator version 2023.3 and for the DUT, which is preferred component interconnect express PCIe solid state drive SSD controller. The virtual lab PCIe version 1.9.0 was utilized to function as a host interface solution. The test scenario is as follows. One photo-to-page operation scenarios NAND performance sequential write and read operation comparison were made among 1. Conventional NAND VIP and 2. A remodeled scheme to apply to the NAND VIP. In addition, in an additional experiment, we conducted the physical NAND device board, which had already been developed, to an external port of the emulator instead of using the VIP. The purpose of this experiment was to measure the performance under the same scenario. The reason behind using the physical NAND device for this experiment was that it's considered the most accurate indicator of the maximum test performance and when evaluating the design with an emulator. So the table 1 is the experimental detail. So the section B is the experimental result. Based on the experimental result represented in figure 7, the conventional NAND VIP completed 7.38 milliseconds of the simulation per hour, whereas the redesigned NAND VIP achieved throughout of the 204 milliseconds per hour, thereby demonstrating by approximately 27-fold improvement in simulation performance. Two I/O parameters measurement also exhibit a similar tend to observe the simulation performance when compared to the performance of an already developed physical NAND. The redesigned NAND VIP attained approximately 67% of the actual NAND performance. Considering the advantage of the debug capabilities such as checkers and the debugging signals inherent to VIP, which are difficult to quantify numerically, it can be expected during the initial development of SoCs associated with the realistic memory specification described in Section 2. Rapid verification cannot be achieved using the VIP instead of a prototype memory which has yet to be manufactured. Figure 7. Experimental result of the simulation performance. Conclusion. Chapter 5 Conclusion. This paper represents a design approach to accelerate the simulation performance of SoCs requiring frequent data interaction verification, such as a NAND controller. To achieve this, we propose a declaration of the appropriate data type of minimized repetitive communication between the emulator and simulator. An FSM can operate on interfaces capable of acceleration of the emulator. So additionally, to minimize the time-consuming areas on the test side, we rewrote the AC-timer functions using synthesizable syntax. Experimental result demonstrated that the redesigned approach achieved 25 times faster simulation performance compared to the VIP prior to redesign. This suggests the potential for efficient early verification of the memory controller functions. Okay, today I read this paper. The design scheme for emulator-friendly memory verification IP to accelerate the simulation performance from DVCON 2025. Thank you for your time. See you next time.